Welcome to the presentation on vision language neural graph featurization for extracting retinal lesions. First, I will explain the background and motivation of our work. Retinopathy encompasses a group of retinal disorders that can lead to severe visual impairment or even blindness. Fundus images are analyzed for the diagnosis of retinal lesions. However, as you can see in Figure 1, retinal lesions exhibit heterogeneous morphology, which poses a significant challenge in developing a robust diagnostic system. The existing systems exhibit multiple limitations, such as supervised methods require large, expertly annotated datasets. They also need to be explicitly fine-tuned for multi-vendor scans. Additionally, small or early lesions, such as microaneurysm, are frequently misclassified. To address these limitations, we propose an unsupervised neural graph featurization method that can extract retinal lesions from fundus scan regardless of scan specification, dataset variation, or vendor-specific artifacts. The proposed method does not require any exhaustive training, fine-tuning, or ground truth labels. Furthermore, its segmentation capability is inherently robust to variations in scanners and imaging conditions. The proposed approach, vision language neural graph featurization, is illustrated in this slide. The proposed approach consists of four main components: segmentation of fundus scan into superpixels, agency network construction, neural graph featurization, and vision language model-based lesion categorization. As we can see in Figure 2, the proposed approach begins by extracting fundus patches from the scan and generating small superpixels using simple linear iterative clustering. Our agency network is constructed by decomposing these superpixels into an undirected graph. The neural graph featurization is then applied to iteratively upload the features of the nodes and edges. A normalized cut is performed once the convergence is achieved, and it results into two separate clusters of lesion and healthy pixels. So these differences are shown by yellow and blue color in the figure. Once we achieve the cluster, they are categorized into different lesion classes using vision language model. The detailed overview of each component is discussed here. The Figure 3 shows the agency network construction. In panel A, the superpixels are decomposed into graph nodes, for example V1, V2, V3, and V4. In panel B, these nodes are connected to undirected edges to form a complete graph. In panel C, we derive a Hamiltonian path to traverse the graph. It starts from V1 and visits each node only once. Finally, the panel D shows that nodes are initialized with feature vectors generated by assigning the superpixels to pre-trained encoders. Similarly, edge descriptors are computing by taking the difference between a node, for example V node, and its adjacent node U, and this difference is passed through an encoder to generate the edge embeddings. The Figure 4 shows the visual representation of the neural graph featurization approach. This approach is used to model a relationship between the lesion and non-lesion regions. This process iteratively updates and propagates features across the graph at iterations, facilitating the refinement of both node descriptors and edge connections. The different iterations are shown in the figure, and you can see in the figure after the convergence, two distinct clusters of lesion and healthy pixels are formed, and once the convergence is achieved, we perform a graph cut to partition the graph into two disjoint subgraphs. The last step of our approach is the categorization of these lesions. For this purpose, we use a simple form-based zero-shot classification. For this purpose, the output of the proposed neural graph cut is fed into a pre-trained vision encoder, and text template is assigned to a pre-trained text encoder such as BUD. These two encoders generate visual and textual embeddings, and the cosine similarity is computed between the visual and textual embedding to find out the class of the lesion. Now we will move towards the experimental results. The proposed method is rigorously evaluated on 4 public datasets and compared with supervised methods. The performance analysis shows that it outperforms the state-of-the-art learning supervised method in terms of F-score precision, recall, and IOQ scores. Moreover, we also perform a few shot analysis by fine-tuning the nodes and edge encoders using 20 samples from IDRID datasets. The result shows that the performance of zero-shot method is comparable to few-shot method. We also conducted a series of experiments to evaluate various ablation aspects of the proposed method. Table 3 presents the evaluation of SLIC across different segmentation value, and we find out segmentation value is equal to underperforms the best for all the datasets. Likewise, we assess the trade-off between the performance, cost, and efficiency. We also evaluated different retrained models within the proposed framework where PVT performs the best, and the results are shown in Table 4. Finally, Table 5 summarizes the convergence result for different sigma threshold and window length K across different datasets. We also qualitative analysis analyze the results. The figure 6 illustrates how accurately the graph are constructed from superpixels of different sizes using the proposed scheme. The figure 7 shows the classification ability of the proposed zero-shot method, and it shows that the proposed zero-shot method can accurately detect and classify different sizes and type of lesions. A shows the fundus image, B shows the contour overlap on the fundus image, C shows the few-shot method results, and D shows the zero-shot method results. To conclude, the proposed method doesn't require any training. It outperforms state-of-the-art supervised learning approaches. In the future, we aim to extend this work to broader medical application and enabling segmentation and classification of small size subsets. Thank you.